In this session, we will discuss about the radioactive decay as well as how to calculate the half-life and binding energy. So, radioactive decay is a random emission, random and spontaneous emission. Random means there is no order. We cannot predict which atom, which nuclei will decay and how much time it will take. And spontaneous means it is not affected by external conditions such as temperature, pressure, state of a radioactive material does not decide how many radiations are coming out. Rate of decay, how many radiations a radioactive sample emit out every second, that is called a rate of a decay, or also we call that as an activity. And activity is basically rate of change of radioactive decay. So we can say that activity is directly proportional to number of the nuclei present. If we have greater number of a nuclei present, means we will have the higher activity. Like if we have sample contain 100 radioactive element at nuclei, another sample contain 50 radioactive nuclei. So the one which is having higher number of radioactive nuclei will emit out more energy, more radiations per second as compared to the one which is having few radioactive nuclei. So activity is directly proportional to the original number of the atoms or radioactive nuclei, and whenever we replace the proportionality sign, we replace with equal to and constant. So activity is equals to constant here, lambda is a constant, and n. What is lambda here? Lambda is known as a decay constant. And the unit of this lambda, it is time inverse. So activity is lambda into n. And if you want to calculate the activity, it is change in the nuclei divided by time interval, we'll get the activity. So greater number of the nuclei, greater activity, greater the value of the decay constant, or bigger the value of the lambda decay constant, it means it will have a higher activity. And the unit of the lambda is second inverse. Then what is the concept of half-life? Half-life means time taken by half of the radioactive sample to decay. We call that as a half-life. Like example, we know activity is equals to lambda n. And whenever we write this equation, we write negative. What is the purpose of this negative sign? Negative sign shows that the activity always decrease, it can never increase. Because in the beginning, you will have always have more radioactive nuclei as compared to after certain time interval. So activity is denoted by change in the nuclei. So we can say delta n divided by delta t activity, and that is minus lambda in n. So when we simplify this equation and take ln and simplify this equation, so the formula which relate the activity, the decay constant, that A is equals to, after simplifying this equation, integrating and taking ln both sides, so A is equals to A naught e raised to power minus lambda t, and n is equals to n naught e raised to power minus lambda t. So this is representing, this is the equation for activity. Like activity after certain time interval is equals to original activity multiplied by e raised to power minus lambda t. And same thing, number of the radioactive nuclei present after certain time interval, that is n, and n naught is the original number minus lambda t. So when we simplify this equation, this is the equation which either we can use it for activity or for the number of the atoms present. So after half-life, half-life means time taken by half of the radioactive sample to decay. So after half-life, this n will be n naught by 2. So if originally is n naught, after half-life it will be n naught by 2. and e raised to power minus lambda, and this t, this time will be half life, t half. When we simplify this equation, n naught will cancel with n naught, so it will be 1 by 2 is equals to e raised to power minus lambda t half. When we take ln both sides, so if it will be ln 1 by 2, or we can say ln 2, we can say 2 raised to power minus 1, or we can say ln 2 or minus ln 2 is equals to, when we take ln for e, so it will become minus lambda t half. Negative will cancel with negative, so ln 2 divided by lambda, so ln 2 divided by lambda, the decay constant, that will give us the half-life, the time taken by half of the radioactive sample to decay. And ln 2 is 0.693, so we can say 0.693 divided by lambda is equals to half-life. And half-life is the time taken by half of the radioactive sample to decay. Or if we need a lambda, the decay constant, then 0.693 divided by half-life, we can get this decay constant. So using this equation, we can work out the decay constant as well as the half-life. So example, a radioactive sample which decay exponential graph is there, exponential change. So the maximum original activity is A naught. So after half-life, its activity will be, because if originally is A naught, after half-life, the time taken by half of radioactive sample to decay, so its activity will change half of its original value, so it will become A by 2. Then after another half-life, its activity will change to A by 4. After another half-life, its activity will change to A by 8. After another half-life, its activity will change to A by 16. So after every half-life, its activity changes half of its original value. The function for activity relating the new activity with the original activity is A is equals to A naught e raised to power minus lambda t. Or if you want to find the number of the radioactive nuclei present after certain time interval, this is not the number decayed. N is the number of the radioactive nuclei present at certain time interval. So n is equals to n naught e raised to power minus lambda t. So example, a sample prepared from this object gives a corrected count rate of 10.9 becquerel. Corrected count rate, because what we have originally, we'll have a background count and we have the count from the source as and background. So when we take a difference between the two, so we'll get only the counts from the source, and we call that as a corrected count. And the corrected count rate for a sample obtained from a living wood is 29.6. So we have two samples. One sample, like our old sample is there, which is giving a 10.9 becquerel, and there's another living wood which is giving 29.6 becquerel. Two samples have the same mass, so it means they have the same particles. Calculate the age of ancient object. Assume that the half-life of carbon-14 is 6,000 years. So how we can work out this? We'll use the formula. First, we'll find a decay constant. The decay constant is ln 2 divided by t half, ln 2 divided by half-life 6,000. So because if we are using here years, so the answer here, it will be year inverse, because it is a unit is like time inverse. So if it is time is in second, it will lambda will be in second inverse. Time is in minutes, minute inverse. Time is in hours, it will be hours inverse. So same thing for year. So we work out the lambda, and we have the formula A is equals to A naught e raised to power minus lambda t. So we know active, because we have two samples, identical samples are there. One is having an activity of 10.9 and the living sample is having an activity of 29.6. So we consider when this plant was alive, it will have the same activity as 29.6. So originally it will have 29.6 because that is comparative activity, but now it is 10.9. So basically 29.6 convert into 10.9. So we will find how much time it will take, and that time is basically the age of this sample. So A is equals to A naught e raised to power minus lambda t. A is equals to 10.9, A naught is 29.6, e raised to power minus, we just substitute the value of decay constant, and finding solving for t. So we work out it is about 8650 years. So using this formula, we work out the age of the sample. In this question, we have half-life of lead is 3.83 into 10 to the power 4 second. Show that the decay constant or lambda is about 2 exponent minus 5, hence calculate the fraction of a sample remain after 1 day or 86,400 seconds. So how to get a decay constant? Decay constant lambda is equal to L naught divided by T half. We have the half-life. We just substitute the value. We'll get the lambda, which is 1.8 into 10 to the power minus 5. Then how much sample? The question is how calculate the fraction of original sample which will remain. We need a fraction. We have the formula n is equals to n naught e raised to power minus lambda t. Fraction, like compared to original, how much left? So we need fraction of the sample, we need n by n naught. So n by n naught is equals to e raised to power minus lambda t. We have lambda, we already worked out, and the time. Look, remember one thing, that if lambda is in second inverse, time should be in second. If lambda is in minute inverse, time should be in minutes. Lambda is in hours, r inverse, the time should be in hours. So e raised to power minus lambda t, we have the value for lambda, we calculated, and we have the time which for after 1 day we are finding. So what fraction will be left after 1 day? 0.20 or zero point 0.2 of a fraction will be left after 1 day. Like compared to the original sample, only 0.2 will be left as radioactive, and most of it will be decayed. So n is a number of the radioactive atoms present after certain time interval, and n naught is the original number of atoms. If we want to find the power in the radioactivity, so energy in joule multiplied by activity will get the power, because power is energy divided by time. So the formula power is energy divided by time. So energy multiplied by activity, or energy multiplied by number of radioactive nuclei decay per second, we will get the power. So some question they ask to calculate the power. So polonium is an alpha emitter. Alpha emitter means majority of the radiations are alpha. Alpha particles are released with the energy of 5.3 mega electron volt. This is the energy released. The activity of the polonium is 8 into 10 to the power 13 becquerel. Means every second this many radiations are coming. Calculate the rate at which energy is transferred from alpha particle in a decay process. So how rate of energy transfer means power, and power is energy, because as you can see, alpha particle, when there is an alpha particle emission, this one energy is released. When one alpha particle emission occurs, this is energy release. But every second 8 into 10 to the power 3 becquerel, that is the number of radiations emitted out. So it means this whole this activity will be multiplied by energy of each, will get the total energy release, and that will be every second. That's why we are calling this as power. So energy multiplied by activity, energy of one multiply, but this energy in joule, so mega electron volt, we have to convert into joule. So 5.3 mega means 10 power 6, so it will be 5.3 into 10 power 6, and 1 electron volt is equals to 1.6 into 10 power minus 19 of the coulomb or joules, that is energy. 1 coulomb is the charge of 1 electron is 1.6 exponent minus 19 coulomb, that is, but here 1 electron volt is 1.6 into 10 power minus 19. So to convert electron volt into joule, so it will be 1.6 into 10 power minus 19. We multiply, so this whole we just multiply to get answer in joules, and that multiplied by activity, the number of the emission every second, So we'll get the power, because SI unit of energy is joule, and joule divided by second, joule divided by second is equals to watt. That's why we have to convert energy into joule. So it is 670 is 67.8 watts. So this is the same as uses of radioactive isotope, the carbon dating. What we do in a carbon dating, like we have a sample of a fossil which we found, and we compare with a new fresh sample, and we compare, example, if the fresh sample of the fossil is having an activity of 20, and the old sample which we found, the trace of this fossil, say its activity is 15 becquerel. So using the half life of the carbon, we work out what is the age of this sample. That is refers to carbon dating. Then a nuclear energy can be released by two ways. One is called nuclear fission, another one is called nuclear fusion. Nuclear fission means when the heavy nucleus break down into lighter nuclei, we call nuclear fission. And fusion means when the lighter nuclei join to form a heavy. So when the particles are present in the nucleus use energy, and the energy which the nucleus use to bind these particles, we call that as binding energy. Like example, inside the nucleus there are proton and neutrons, and nucleus used energy to hold these particles. So when the nucleus is using them to hold these particles, we call this energy as a binding energy. But how we are sure, how we know that this there's a binding energy, or there's the energy used by the nucleus to hold these nucleons? So example, if we have two protons and two neutrons outside the nucleus independent, so because each is having, proton and neutron have the same mass, which is 1 atomic mass unit, or 1.6 exponent minus 27. So the total mass is equals to 4u when they are outside. But the same number of nucleon when they are present inside, when we have two proton and two neutrons inside the nucleus of an atom. So what we observe the mass of the nucleus is not 4u, it is less than 4u, maybe example 3.9u. So why this happened? When they were independent, when the particles were independent outside the nucleus, they were having more mass. But as these particles are inside the nucleus, their mass appear to decrease, because if the mass of nucleus decrease, it means the mass of particle decrease. So the this mass decrease or change in mass, what we call that as a mass defect. And what happened, why there is a mass defect? As some of the mass is converted into energy, and that energy is used to hold the particles within the nucleus. Otherwise these particles cannot be together. So energy, some of the mass has changed into energy, and that energy we call as a binding energy. So binding energy is energy needed to bind the nucleons within the nucleus. So whenever you have particle outside the nucleus and particles inside the nucleus, always you will find the difference in the mass, and that difference in the mass is known as mass defect. And why there is a mass defect? Because the mass can change into energy, the matter and energy are can be converted into each other. So mass converted into energy, and that energy is the binding energy. And there's also another term we call binding energy per unit mass. So binding energy divided by mass defect will get binding energy per unit mass, or binding energy per nucleon as well. So the binding energy divided by number of the nucleon will get the binding energy per nucleon. So particles outside the nucleus will have different mass as compared to particles within the nucleus. So this binding energy, if a nucleus is having a higher binding energy per nucleon, it means its nucleus is more stable. This is a word example. As you can see here in the figure, you can see a nucleus of a carbon nuclei. Uh, when the total mass of a carbon, we subtract the mass of electrons, so we get the mass of the nucleus. This is the mass of the nucleus. And when we find the mass of 6 neutron and 6 protons, this is the total mass of 6 neutron and proton. So when the particles are independent, they have more mass as compared to when they join within the nucleus, cluster within the nucleus. And when we calculate a difference in the mass, we call that as a mass defect. And how to know how much energy will be released? So after getting the mass defect, that is in U, atomic mass unit, will convert into kilogram by multiplying with 1.66 into 10 to the power minus 27. So this is kilogram. So 1.64 is a mass defect. And we can also find, using this mass defect, we can also find the energy and the binding energy per nucleon. So E is equals to mc square, will get the energy. So you can see this is a graph which shows the binding energy per nucleon for different elements, and the peak, iron is at the peak, the highest. So it means the most stable nucleus is hydrogen, is iron. And that is the reason lighter nuclei, why lighter nuclei undergo fusion and the heavy nucleus undergo fission, because when lighter will join together, like hydrogen turn to helium, helium turn to lithium, lithium to oxygen, and then to iron. So they can be stable. Same way uranium break down into lighter, uranium break down into krypton and tin, and they reach iron. So what will happen? By fission reaction, they can only break down and reach iron, and lighter nuclei by fusion reaction, they can only combine and turn into iron. So lighter nuclei undergo fusion reaction to reach iron, the stable, and heavy nucleus break down to form iron so that it will be stable. So iron is having the highest binding energy per nucleon, which is about 8.6 mega electron volt per nucleon. So as you can see, the high binding energy per nucleon means more energy is needed to remove the nucleon from the nucleus. So means the nucleus is more stable. Isotopes with the highest binding energy per nucleon is iron 56, which is about 8.8 per nucleon. And it is a most stable nucleus. And any nuclear reaction which increases the binding energy per nucleon will give out energy, and two of the reactions are typed, like when small nuclei combine to make a larger nuclei with a greater binding energy, we call that as a fusion, and when the larger nuclei break down to smaller, it will be called that as a nuclear fission reaction. So what happened in a nuclear fission reaction? In a nuclear fission reaction, a large nuclei break into a smaller, and it release energy in some of the neutron, and it is always like a chain reaction. So you have a large nucleus, you target by a neutron, it break down into lighter nuclei and further give out neutrons, and these neutrons initiate another reaction, another fission reaction. So that's why fission reaction is a chain reaction. We started with one and it multiplied, and the process is spontaneous if it occur at its own, and it can be induced by making a neutron enter to the nucleus. So it can happen both ways. It can be spontaneous fission, it can be a induced fission. Induced fission means we force the nucleus to undergo a fission, and the larger nucleus, the more unstable nuclei will be, because you can see the binding energy per nucleon here, the binding energy per nucleon is less as compared to iron. That's why it is unstable, and it can only be stable by releasing or converting into lighter nuclei. And what happens in a fusion reaction? So in a fusion reaction, the two lighter nuclei combine together and it will create a large nucleus, and it also release energy. So both nuclear fission and nuclear fusion both are exothermic, both release energy. So using of nuclear fusion to produce energy is much more efficient than fission. What is the reason for that? Because the fuel from the fusion reaction is virtually infinite. Like we have infinite number of hydrogen and helium atoms. So hydrogen required to fuse into helium is available, and whereas fission rely on uranium, and uranium amount of uranium is limited. We don't have too much uranium. And another advantage of producing the energy by fusion, there is no radioactive waste. But in case of when we are using the heavy nuclei, they are mostly radioactive as well, as their nucleus is unstable. So no radioactive waste produced. The helium produced would be inert. And but the problem with fission is radioactive. It produces a radioactive waste, and we have the disposal problem or storage problem. And for a given mass of a fuel, energy released by fusion is much more greater than energy released by fission. And there is a little possibility of runaway fusion reaction, unlike fission. Basically, like what happened, fission reaction sometime it is uncontrollable, like it multiplied exponentially. As a result, what happened that we are not able to control. But fusion, it is little possibility that it might be uncontrollable. Mostly it is controllable. But what is the problem? What are the difficulties of making a nuclear fusion feasible? Because you want to fuse the two nuclei. If you want to fuse the two nuclei, so you have to make them closer. And to make them closer, we need a very high temperature, because nucleus of an atom, these are identical protons, are there like charges, so positively charged, and they are repelling. So as they're repelling, we need lot of energy to bring the two nuclei closer, so we need a high temperature. And for sustainable fusion, we need a high density, so that more molecules or more particles or more nuclei can combine. And if the proton touch the wall, like the problem is with the fusion, practically the fusion reactor, that if these particles will come in contact with the wall of the container, they lose their energy and the fusion reaction stops. So we need a very strong magnetic field to confine. Like, say this is a chamber, this is a container in which we undergo a nuclear fusion reaction. So we apply a magnetic field so that these particles does not collide with the wall. Like they will stay away from the wall. Why? Because if they come in contact with the wall, they lose their energy to the surrounding without undergoing a fusion reaction. So that will leads to no fusion. So we, for this purpose, for confinement, the confinement of the plasma or the fuel for nuclear fusion reaction, we need a very strong magnetic field. But these conditions are possible on the sun or different star. That's why sun is producing the energy like light and heat energy by nuclear fusion reaction. But on earth, small scale fusion can be done, but for a large scale fusion, it is not possible. There are fusion reactors, but practically we are using fission reactors to produce energy by using the nuclear. Is it clear how nuclear fusion compared with nuclear fission? So this was about the nuclear decay as well as the radioactive emission. So nuclear fission, in this topic you have to learn like how to calculate the binding energy per nucleon, the mass defect, the radioactive activity, radioactive emission, comparing the nuclear fission with fusion. and some advantages of nuclear fission or fusion, nuclear fusion over fission, and why, what are the conditions which are we need to have a sustainable nuclear fusion reaction.